my colleague William Ratcliffe always says that neutron scattering is it's the beam time for civilized experiments.
So now we, by the way,
my colleague William Ratcliffe always says that neutron.
Okay, now we're online.
Yeah, well, now we're live online. Yeah.
Hartmut once told me that if you're at the ILL in Grenoble, you start a measurement, you go skiing, you come back, you collect your data. That's
good. That's good. You see, this is where.
This is the dream. It's one of those things where everyone's trying to get more intensity, and actually that's going to come up today. But all the instrument scientists are kind of like, oh, but not too much, you know, because then we have to change samples every 2 hours. Exactly. I don't know if I want to do that.
Okay. We still need 8 hours.
Too much work.
Yeah. 8 hours is a really good experiment time.
These neutrons are very useful. So, but I also want to know what is the new things with it, because it's such an old tool, but now it's, you know, the new things is really what it was useful. When we talk, I remember that there's quite a few things that I didn't know that I've done now, which is really useful to know.
I think it's always
even for a theorist, yeah.
I think it's always scary when you look at old papers on antiferromagnets, because there's always a paper from 1969 on neutron scattering on the bulk crystal of that compound.
Yeah.
Oh, yes. Yeah. Every antiferromagnetic system, you end up going back to some paper from the 70s and looking for the order parameter.
Exactly.
Nicholas is not here yet. Okay. I think Brenner's will show up shortly. Let me.
I'll go back to the background. I'm looking forward to learning about new stuff from neutrons.
Okay. So I think we're now on time. Okay, so let me share my screen real quick. Okay. So thank you everybody for joining us once again to the online SPICE-SPIN+X seminar series that we have here, organized by myself and Karin City from Duisburg University now, in collaboration always with SPIN+X, SFP Collaborative Research Center led by Martina Schliemann and Burger Hillebrand in Kaiserslautern and Matthias Chloe here in Mainz. As you know, this is a Zoom webinar. Please write your questions on the Q&A or raise your hands, and I will give you the floor to ask the questions to the speaker afterwards. And check the next the continuing talks that we'll have over the next weeks as well and months. So today we have very young Alexander Grutter, who is a permanent staff member at NIST in the Neutron Research Facility. He graduated from Case Western University and got his PhD in 2013 from the University of California in Berkeley. And then now it's not so much in the sunny side in the West Coast, but in the East Coast. And then he's been on the forefront of neutron scattering reflectometry. And then this is some of the things that he will share us today. So I will stop sharing and I will ask you please to go ahead and start sharing your talk and start whenever you like.
Okay. Can you see this?
Yeah.
Okay, wonderful. So yeah, thank you so much for the opportunity to be here and talk to you today about some of our work in trying to unravel the complexity of proximity, magnetization, and topological surfaces, and in particular with next generation neutron reflectometry. So the neutron reflectometry part is very important. I'm an instrument scientist at the NIST Center for Neutron Research, which means that there needs to be a really big caveat or disclaimer to this talk, which is that I am in no sense a theoretical expert on topology or electronic structures, right? I throw neutrons at materials and I watch those neutrons bounce off and I see what they do. So for me personally, I'm much more comfortable thinking about non-trivial topology in terms of like real space structures like skyrmions, where you can actually see where the topological protection is coming from, actually see the winding behavior in the spins themselves. But of course, there's a huge amount of interest right now in the sort of topology and non-trivial topology of electronic states, like the kind of magnetic field induced non-trivial topology that gives you the quantum Hall effect. So although this is not my area necessarily of expertise, theoretically, I've been very lucky to have many collaborators who patiently attempted to explain these things to me. And so if I say something that doesn't make any sense about the topology of these systems, then it's my fault, not theirs, for failing to absorb the instructions. But fortunately, we don't really need to go into the deeper theoretical aspects of topology and electronic states. What I really want to be able to say at the end of this discussion is that, you know, audience members can hopefully answer, I'd like to say all of these questions, but we'll say that if you can answer 2 of these at the end of the discussion, then we'll have done a pretty good job. So what I want to give you a sense of is, why does anyone care about magnetic proximity effects in topological insulators? Are there actually real extant and demonstrable MPEs in topological insulator systems? How do we currently characterize and understand these effects? And in an ideal world, how do we wish we characterize them? How should we characterize magnetic proximity effects? So of course, we need to begin with a very brief discussion of topological insulators. Almost all of this discussion is going to be focusing on the sort of canonical topological insulator family of bismuth selenide, bismuth telluride, bismuth antimony telluride. And the main points you need to know is that these are insulators in the bulk, but they have conductive surface states that are confined to approximately 3 nanometers near the surface. Now, these surface states appear at both the top and bottom of the material. And this, of course, means that if you have a topological insulator below 6 nanometers thick, then you start to get some weird hybridization effects between the top and the bottom. And in fact, the hybridization can destroy the topological surface states. But assuming your topological insulator is thick enough, what you should see is that in between your bulk valence and bulk conduction bands, and this has been seen many, many times in ARPEs for a variety of different systems, you should have a Dirac cone with a linear dispersion relation connecting effectively the bulk valence and conduction bands. And in this state, you have all kinds of really, really interesting properties and interactions. And this is characterized by very, very strong spin orbit interactions, and which gives you spin momentum locking, so that your conduction channels are in fact spin dependent. You can do all kinds of really interesting things with these topological surface states. One of the main attractions that we're not really going to get into here, but is still very important, is a very high spin orbit torque efficiency. So what people have been doing, and here I'm just pulling an example from a paper by Peng Li in 2019, but of course this has been extensively studied by many groups. What people are interested in doing is switching a magnetic material, in this case often it's a magnetic insulator, by flowing a current through your topological insulator. And so you can actually achieve very high efficiency magnetic splitting, magnetic switching. And this is a consequence, actually, this is one of the things that Peng was showing, is that as you cool down and the topological surface states more and more dominate the conductivity of your topological insulator, you get really large efficiency gains and can massively outperform, say, switching via platinum. But you can also stabilize really interesting novel quantum states, like, for example, the axion insulator state, where you get quantization of your Hall conductivity and a quantized zero longitudinal conductivity. But the quantum state we really want to sort of be focusing on as a motivation, not that it's in any sense the only important quantum state in topological insulators, but the one we're going to be focusing on the most today is the quantum anomalous Hall effect. And this is something that was originally demonstrated in 2013 by Suizhu Chang et al. And the basic idea is that, okay, you have your Dirac cone, your topological surface state, and you want to induce magnetization in this topological surface state, in the topological insulator. So bismuth selenide and bismuth antimony telluride, they're not naturally magnetic, but it turns out that you can dope them. So you put some chromium or vanadium dopants into the system, and you get a net magnetization. And what this does is break time reversal symmetry and opens up a gap in the surface state. And I'm borrowing this very nice figure from Liu and Hejjedal, who wrote a very nice review article on this topic recently. And what you can, and this band gap, or this gap in the topological surface states, have also been observed in a number of different places in ARPES again. And so you can see this right here. And once you've done this, once you've broken time reversal symmetry and you cool down the system to really, really, really cold temperatures in the sort of hundreds of millikelvin regime, what you get is quantized edge conduction. And that is the quantum anomalous Hall effect, which is characterized by a Hall resistance of plus or minus 1 h over e squared, and a longitudinal conductivity of 0. So this is this state is very interesting for a whole host of different applications in sort of quantum electronics. The idea being you have this really neat non-dissipative transport channel around the edge. And people are very interested in trying to incorporate this into real devices. And one of the real barriers to doing so is the quantization temperature. So people have been working on these chrome and vanadium doped structures for, I don't know, close to a decade now, and trying to reduce or trying to increase the quantization temperature. So what this means is that basically, as you cool, you don't really achieve a fully quantized quantum anomalous Hall state until usually you're below a few hundred millikelvin. In some really nicely designed modulation dope structures by Mogi et al., they were able to push this up to around 2 Kelvin. And but that's about it. And there are a lot of sort of potential explanations for this behavior. And one of them that's very often cited is dopant inhomogeneity. So the idea that, sure, really close to your chromium or your vanadium dopants, the gap induced in the surface state by your magnetic moment is quite large. And this has been demonstrated a number of times. But you have a tendency to have dopant clustering. It's not uniform. Maybe further away from your dopant, you have a much smaller gap. And so since it's not uniform, your overall effective gap in the surface state is relatively small. And so your quantization temperature is also quite small. And some really interesting work by Lachman et al. In 2015, they did scanning squid measurements that showed that you have, in fact, all these sort of super paramagnetic regions rather than a single uniform magnetic state. Now, on the other hand, some recent theory calculations by Chi et al. Demonstrated that you also have to worry about the inhomogeneity in the crystal itself. So bismuth and antimony in bismuth antimony telluride have a tendency to cluster themselves so that you don't actually have a homogeneous mixing, but you have some bismuth and some antimony, and this can lead to variations in Fermi level position and gap size as well that can cause problems with and suppress your quantization temperature. You also have to worry about preferential substitution of your magnetic dopants on specific sites, and also topologically trivial conduction pathways. And here it's sort of helpful to look at this really nice diagram from Pan et al., where they were trying to understand where this suppression behavior, this suppressed quantization temperature comes from. And one of the things that they pointed out is that, you know, the actual shape of the valence band and the conduction band is kind of complicated. And if you're not really careful with your structure design, you can get cases where the bulk band actually overlaps with the gap in the surface state. And so the Fermi level then passes right through the bulk band all of a sudden, and then your topologically trivial conduction pathways dominate. And this can also happen if you get a lot of dopant-induced defect conduction states that are sitting right in the middle of the exchange gap as well. So one of the things that people have suggested to improve the uniformity in these systems is we'll just increase the number of dopants until it's quite uniform. And this should increase your Curie temperature and also your gap sort of size and uniformity. But on the other hand, it's a double-edged sword, right? You also are increasing the number of defect states, which can then give you more trivial conduction pathways. You're weakening the spin orbit torque that actually gives you your band inversion in the first place. And you also will eventually reach the solubility limit of your dopants. And so at that point, you're just sort of stuck. You can't go any further. So there's a lot of challenges. And one of the directions people have gone in order to address this is to look at manganese bismuth telluride or other intrinsically magnetic topological insulators. So instead of doping now, we're looking for a material that has an intrinsic long-range magnetic order. And in this case, basically you have a structure that looks something like this. You have manganese monolayers separated by a bunch of bismuth and tellurium, and these are antiferromagnetically ordered. But you can break the symmetry with a large magnetic field and get all of these magnetic moments to point in the same direction. And so if you do this, you can in fact achieve the quantum anomalous Hall effect as demonstrated by Deng et al. But of course, and so they found a zero field quantum anomalous Hall effect at 1.4 Kelvin and in a high magnetic field up to 6.5 Kelvin. So this is a huge improvement, but it's still lower than you might expect from theoretical calculations of how big the exchange gap is. And in fact, there are many concerns about the exact same sort of problems that you end up with in doped systems. So for example, magnetic inhomogeneity and defects, manganese likes to move around a lot in these materials, and you can have a lot of anti-site defects. And so this can also, reduce homogeneity, reduce your defects, and also give you more trivial conduction pathways through defect states. So again, we're making a lot of progress. And in fact, I'm looking here at another figure borrowed from the same review article that came out in 2021. You can see that they're increasing the zero field quantum anomalous Hall temperature is increasing pretty quickly with time and culminated at around 7 Kelvin in superlattices of this manganese bismuth telluride and bismuth telluride. It's also been found in twisted bilayer graphene, but even so, we're limited still to 7 Kelvin, and we should be able to go higher. So the question becomes, how do we strengthen magnetism in these systems and get something more uniform while reducing the defects? And here it's useful to start thinking about magnetic proximity effects. So all we really are interested in is getting the surface of your topological insulators like bismuth selenide, bismuth antimony telluride, all to magnetize. We really just need to induce a gap in the surface state. And one of the ways we might do that is by taking a really nice uniform magnetic material and growing a thin film heterostructure so that there's an interface between this large reservoir of magnetic order and the topological insulator itself. And then through a combination of direct exchange or overlap and charge leakage, you can actually get a magnetic spin polarization to be induced in the topological insulator at the interface. And this also will effectively induce a gap in the surface states. Now, it should be pointed out that there are a lot of different ways of looking at the exchange interaction of magnetic proximity effects. I don't really think we need to get into the details of that here, but the basic idea is that some form of electronic interaction, whether it be direct orbital overlap or leakage of the topological surface state into the magnetic material, some interaction there spin polarizes your topological surface state and induces a gap. And this has been tried since 2013, 2014, and everything from yttrium iron garnet to europium sulfide to chrome antimonide. And in fact, the Takura group in 2019 successfully realized the quantum anomalous Hall effect in bismuth antimony telluride interfaced with zinc chromium telluride. And this is a doped ferromagnet here. Now, one of the really interesting things about this system is that it's got tellurium-tellurium bonds across the interface. And this is thought to be a really important part of the approach, and part of the reason it succeeded is that potentially the tellurium-tellurium interface gives you a very nice alignment of your bands across the interface and a stronger interaction. But on the other hand, the quantization temperature is still unfortunately rather low. Let's say around, well, certainly below 1 Kelvin. And it has been suggested that this might be because that you're still experiencing dopant-related inhomogeneity in this system. So the idea being, okay, well, now you no longer have chromium dopants that are randomly dispersed in the bismuth antimony telluride, but instead they're just randomly dispersed in the zinc chromium telluride. This may or may not actually be the reason for the low transition temperature. We don't really know yet. It could be that there are other explanations, but the vast majority of approaches or attempts to induce magnetic proximity effects in topological insulators have instead focused on uniform magnetic systems, so not doped, but bulk materials that are magnetically ordered. So the thulium iron garnet example I told you about earlier was done by the Xi group, and here I'm citing from Tang et al. In 2017. And what has been really interesting to see is that sort of the uniform magnetic materials interfaced with topological insulators, they lead to the highest ordered, the highest temperature proximity effects reported. So the magnetic ordering that people report in these sorts of systems is quite high. And in fact, often you get reports that are, above room temperature. But on the other hand, there's no, at least as far as I'm aware, maybe something really recent came out, but they have yet to realize the quantum anomalous Hall effect in these systems. And as just a small side note, there is one report that might be quite close, and that's chrome germanium telluride interface with bismuth antimony telluride. They don't quite achieve quantization, but the anomalous Hall effect is very, very large. And so it might be close. So how do we understand this? Well, one of the things we need to try and get our heads around is figuring out, is there a real magnetization induced in the system at all? And here we have to point out that a lot of the measurements that people tend to do on these systems are transport measurements. And so the idea is that you take an insulating material and you flow current primarily through the topological surface states in your topological insulator. And if you see an anomalous Hall loop, the hope is that you're not really probing the insulating state, but just the surface state. And so if you see a Hall loop, then that implies a magnetic proximity effect. Now, this is certainly true that a magnetic proximity effect will give you an anomalous Hall loop, or should. But on the other hand, you can have anomalous Hall loops, say through the inverse spin Hall effect, that don't necessarily originate in a magnetization on the topological insulator, but just through interactions with the thulium iron garnet or whatever other proximity reservoir you're thinking about. So it would be really nice to have more direct probes like X-ray spectroscopy measurements or neutron reflectometry that can directly tell us if there's a magnetization in the topological insulator. And in fact, the Xi group did exactly such a measurement. They did a very, very nice follow-up study in 2019 where they did X-ray magnetic circular dichroism measurements. And they did, in fact, in Chaya Yang et al., they did, in fact, find a dichroism on the tellurium edge that showed a real magnetization in the topological insulator layer, but the temperature dependence appeared to be very different from that of the Hall data, where the tellurium XMCD disappears somewhere between around 80 Kelvin and 200, and we're not sure exactly, they're not sure exactly where that transition is. So it's also sort of an important side note that Just because XMCD can't see it doesn't mean that there is absolutely no proximity effect, right? There could be a very, very, very small magnetization in the TI layer, and maybe it's just below the detection limit of XMCD, but not Hall data. It's kind of hard to know for sure. And the question of how magnetized it needs to be in order to give you a gap in the surface states is a complicated question. But I'll point out also that XMCD measurements on the sort of well-studied europium sulfide bismuth selenide interface with previously reported room temperature magnetic proximity effects, the XMCD also finds nothing in the bismuth selenide europium sulfide interface, which is interesting. Okay, so with all of that background, we sort of have finally arrived at what I actually do, which is polarized neutron reflectometry. And polarized neutron reflectometry is a depth-sensitive probe. So basically, if you have a thin film heterostructure and you want to know which layer is magnetized, that's what neutron reflectometry tells you. And in fact, this is exactly what you want for a study of magnetic proximity effects. So in principle, it's extremely simple. You take your neutron, you throw it at a sample, and our main requirement is the sample be shiny so that it's nice and reflective. And then you collect that reflected neutron in a detector. And you do this with spin polarized neutrons. So you look at the spin up reflectivity, you look at the spin down reflectivity. And you hopefully, if you have a magnetic sample and you collect the reflectivity as a function of angle, you will see a splitting between your spin up and spin down reflectivities. And so we can plot it like this, or we can look at what we call the spin asymmetry, which is just, one minus the other divided by their sum. Okay, so then we fit this data, and in the end, what you're trying to get out is a scattering length density depth profile. Now, rather than get into all of the detailed business of what a scattering length density is and where it comes from, you can think of it as the potential experienced by the neutron. And there are two forms of scattering length density we worry about. One is the nuclear scattering length density, which depends on the composition of your material and its density. So for example, if it's a chrome oxide layer, you have a nice large scattering length density. Bismuth antimony telluride tends to be quite a bit smaller. And if you have a magnetic scattering length density, this tells you your in-plane magnetization as a function of depth. And so what we're getting is thickness of layers, composition of layers, roughness of layers, and where is the magnetization. And I want to start out with an example of exactly how fraught analyzing and understanding this sort of reflectometry data can be. And here I want to show an example of magnesium aluminum ferrite next to bismuth selenide. And this is work done in collaboration with Yuri Suzuki's group at Stanford University, Peng Li at Auburn, and Nitin Samar's group at Penn State. So the reason that magnesium aluminum ferrite was chosen is that it's a very promising magnetic insulator material, actually mostly used for ultra low damping applications. But what's nice is it has little to no dead layers at the surface, so it should have really nice contact of the magnetic layers. It also is very, very insulating, so transport measurements should really primarily probe the bismuth selenide. And it tends to be, relatively sharp and high quality when you grow it. So it's a really ideal candidate for inducing a magnetic proximity effect in an adjacent topological insulator. We take neutron reflectometry measurements, we fit them, as you can see in the solid lines. I would argue this is a pretty good fit to the data. And so intrinsically, you just sort of say, well, that fit is really good. We should just believe what it tells us. Spoiler alert, that's probably not true. And so what we see is in the magnesium aluminum ferrite layer, you have a nice uniform magnetization. And in the bismuth selenide layer, you have a little bump right here. Now, Lauren Riddiford, the student leading this study, who did a really nice job, decided to double check this with transport measurements. And so what she did was take anomalous Hall measurements on bismuth selenide on top of magnesium aluminum ferrite. And so what she finds is a nice nonlinear Hall effect that looks an awful lot like a really low coercivity magnetization where you have some sort of saturation. And so this looks very much like what you might expect from some sort of anomalous Hall effect induced by a magnetic proximity effect, which is in agreement with this little bump here, right? That looks like a proximity effect in the bismuth selenide. So then she decided to check what you get from the transport data when you just grow bismuth selenide on a bare non-magnetic substrate. And the awkward answer is you get something that looks basically the same. So that's a little concerning. And what she then does is try to understand this data and fit it using a two-band model of the conductivity where you have multiple contributions to the Hall effect. And in fact, this fits the data perfectly. And so now we have a problem. So how can we understand where this idea that there's a magnetic proximity effect is coming from in the neutron reflectometry data? Because the transport data says that there probably isn't a real signal associated with a proximity effect. And so what we're doing here is comparing simulated curves from two different models, one with a magnetic proximity effect and one without. And what we see is that as soon as we turn off the magnetic proximity effect, we get a shift in the spin asymmetry right here. And we get a little bit of a shift right here so that we miss regions here and here. And you might argue that this doesn't fit quite as well, but it's kind of hard to say. But anyway, turning off the magnetic proximity effect causes the neutron reflectometry fit to miss in several key places. But what do we really learn here? The proximity effects are very subtle signatures in the neutron reflectometry data, right? This, I think, doesn't always come through very well in the literature, but the signal you get is going to be overwhelmingly dominated by the large magnetization from the magnetized proximity reservoir, so the bulk ordered magnetic system. So while this seems to indicate a magnetic proximity effect, we need to look for subtle alternative models, like subtle changes to the model that might give us the same quality of fit without a magnetic proximity effect. And we can find one almost immediately. In fact, I think this was our first guess, was, well, what if the bismuth selenide has a bit of a weird transitional growth region of lower density at the interface? Well, as soon as we do that, and we model this with no magnetic proximity effect, no sort of bump extending into the bismuth selenide. As soon as we do this, we actually catch this feature perfectly again, and we catch this feature really nicely again. And so it looks like transitional growth regions and interface structures can spoof a magnetic proximity effect. And so, well, how do we separate these two competing models that give us basically the same neutron reflectivity fit? We need to bring in other techniques to separate the two competing models. And so what we did is X-ray reflectivity and transmission electron microscopy, both of which confirm a transitional growth region at the interface and have no proximity effect. So here in the dashed line, you have a proximity effect model, and in the black solid line here, you have a transitional growth region model. So that fits the X-ray reflectivity really well. And in the TEM, you can see a sort of subtle intermixed region of different quality right here that also agrees with this transitional growth region model. And so the point to take home here is that you really, really need to pay attention to complementary measurements, allowing model selection, and try to understand what's happening at the critical interface. And so Lauren's paper is going to be out, I think, very soon in PRL, if it's not already. So how general are these sort of interface quality issues? And here I'm just pulling a couple of examples from recent collaborations where we saw this. It was totally not the point of either of these papers. It's just something that popped up unexpectedly. So here is a collaboration led by Yang Liu and on the NIST Center for Neutron Research side led by Patrick Quarterman in collaboration with the Wu, Samarth, and Wang groups. Where growing yttrium iron garnet and then bismuth antimony telluride again gives you this transitional growth region. And it also appears, again, in a collaboration with here the Ross group at MIT, led by Jackson Bauer and Patrick Quarterman. What we found is that it seems like it may be related to having a vacuum break between the growth of your layers. So the idea being that if you grow your dysprosium iron garnet, for example, and then you grow platinum on top, if you do this in separate chambers and then transfer the dysprosium iron garnet, transfer it through air and then grow platinum, you get a really low density, low quality region right at the interface. On the other hand, if you grow the dysprosium iron garnet and then do an in situ growth of the platinum without any vacuum breaks, you get a really, really high quality interface. And this super strongly changes the coupling right at the interface. But that's not the only thing you need to worry about. And here I want to briefly show some work from the Sun group at Northeastern, led by Nirjar Bhattacharjee. I have to say my involvement in this was very peripheral and basically consisted of just advising a little bit on how to properly fit the reflectivity. All the real neutron measurements were done by Dr. Lauter. But what they found that was really interesting is that you have to pay a lot of attention to the surface chemistry in this system as well. So it's not just looking at low density interface regions, but if you grow, say, bismuth telluride next to permalloy or some other ferromagnetic metal, you may actually get a distinct intermixed region like you see right here. And in fact, Nirjar has reason to believe that this intermixing leads to a completely new phase that may actually include the topological antiferromagnet nickel bismuth telluride, because they see the emergence of exchange bias in this system. And so that's very, very interesting. But of course, it is very much possible to get clean oxide topological insulator interfaces. This has been achieved numerous times, for example, in chromia next to topological insulator materials. And here I'm showing some excerpts from work we did with Kang Wang's group at UCLA. And one of the interesting things here is that this actually involved an ex situ transfer. So the chromia was grown in this case by Christian Binnick's group and then sent all the way to UCLA, where the topological insulator was grown on top. But chromia is phenomenally stable. And what they did was a really high temperature heat treatment in vacuum prior to growth. So this may or may not actually be the key to getting this sort of higher quality interface. It may actually be something to do with the chromia surface itself. We don't know. But what we did definitely find is that you have a very sharp, high quality interface, no transitional growth region, and strong interface coupling. So it was possible to get exchange bias across the antiferromagnetic interface with a chromium doped topological insulator. All right, so with all of that background and the caveats that like interfaces are complicated, being sure about things is hard, I want to show a few examples where I think we maximized our chances of getting a definitive answer to whether or not there's a magnetic proximity effect. And I want to start with a case where we're pretty sure that we have a clear answer of no, there is no magnetic proximity effect. And here we have chromium doped bismuth antimony telluride next to tin telluride. And this is a simple case of no detectable magnetic proximity effect. So these materials are extremely nice. Tin telluride actually turns out to be a topological crystalline insulator. This isn't super important necessarily for the story I'm sharing, although the physics is very interesting. But the leader of the study, Peng Dong, grew these samples with really, really high quality. They're very growth compatible, and you have sharp interfaces with really great crystallinity. And so what he did was he grew 2 nanometers of chrome doped bismuth antimony telluride and saw an anomalous Hall effect, a really strong one. The trick is that chrome doped bismuth antimony telluride should be insulating. And so you don't expect to actually see any signatures of transport through the chrome doped BST. So where is this anomalous Hall effect coming from? And so the question is the chromium doped bismuth antimony telluride inducing proximity magnetism in the tin telluride? And this turns out to be a ridiculously difficult neutron reflectivity problem. And the reason for that is obvious if you look at the nuclear scattering length density profile here, where chromium doped bismuth antimony telluride and tin telluride look exactly the same to the neutron. And so even though we grew a very special sample for neutrons where we have really thick chromium doped bismuth antimony telluride on bottom and a nice tin telluride layer on top, you just can't tell where one layer starts and the other stops. or one layer stops and the other starts from the neutron reflectometry. So what we did was get really high resolution transmission electron microscopy and constrain the thicknesses of the layers using that. And so that's what gives you this blue bar right here. These are the 95% confidence intervals on where the interface between the two layers ought to be. And then we can get the magnetic thickness very precisely from the neutron reflectivity. And so the red line here is telling us where the magnetized region stops. And so because these don't overlap, it tells us that the magnetization doesn't extend into the tin telluride, but it really took combining TEM imaging with neutron reflectometry to figure this out. And so effectively the magnetic thickness is lower than the thickness of the chrome doped bismuth antimony telluride. And we can actually show you a counterexample here where if you force the magnetization to extend into the tin telluride, your fit gets pretty horrible very quickly. So you can see how all of a sudden the red line is not going through like any of the points within error. So there's no proximity effect in this system that we can detect. So now I want to show you an example of a system where we are really relatively confident that we dotted all of our I's and crossed all our T's, and we have a real magnetic proximity effect. And this again was done in collaboration with Kang Wang's group and led by Chaoyao Yang. And this is, I think, the clearest example of a magnetic proximity effect that I've seen personally. And what we're doing is using chromium selenide. Now, chromium selenide is an antiferromagnet. So now we're talking about an antiferromagnetic proximity effect where we count on the spin polarization of the chromium spins at the surface to induce a magnetic moment in the topological insulator. And so we can test that it is in fact antiferromagnetic. Neutron reflectometry of the sample shows of a pure chromium selenide film shows basically no magnetization like you'd expect. But as soon as you grow a chromium selenide layer on top of a topological insulator, all of a sudden you have a spin asymmetry popping up right here. And this gives you a magnetization that appears to be, relatively close to the interface, but it might be kind of biased toward the chromium selenide layer. So this is I'm going to say a candidate for a proximity effect at this point because you have some emergent magnetization that pops up as soon as you grow the bilayer, but it's not totally clear yet, and we need to look at the transport data. The other thing I want to point out is it's much easier to understand what's going on in this system because, as I mentioned before, right, in the earlier example, almost all of your magnetic signal comes from your magnetic reservoir, right? Your large ferromagnet that you grow. But of course, in an antiferromagnetic proximity effect, you're getting much less sort of a confounding signal from the magnetization of your proximity reservoir. Okay, so if we look at the transport data now, we actually got extremely lucky. So when Chaoyao grows these films in different orders, so chromium selenide on top of bismuth antimony telluride gives you a really nice anomalous Hall effect. And on the other hand, bismuth antimony telluride on top of chromium selenide gives you a straight line, no anomalous Hall effect at all. And so this tells us two things, right? First of all, obviously the order of the growth matters a lot. And it's probably not going to be a situation where we have an intermixing induced signal. So one might imagine worrying that the chromium diffuses into the bismuth antimony telluride and what you end up with is effectively a doped topological insulator again. But if that were true, we would expect that to appear to a certain degree, regardless of which order you grow the layers in. And so this doesn't seem like it's in an intermixing type effect, and it's a much better candidate for magnetic proximity. And so the final piece of the puzzle then comes when we do X-ray magnetic circular dichroism measurements to get element-specific magnetic information. And so if we show bismuth antimony telluride on top, we do see a very, very small chromium magnetization. It's like, I would say, trace. But then if we grow chromium selenide on top, it's significantly larger. So the growth again seems to matter here, and you get more of a magnetic signal in the chromium if you grow chromium selenide on top. And if we try to probe the magnetic state of the topological insulator at the antimony edge, what we see is that there's no splitting at all in this case here. And there's a very, very small splitting in this case here where chromium selenide is on top. And so this tells us that we have an actual net spin polarization that is being induced only in the case of chromium selenide on top of bismuth antimony telluride. So how do we understand this? Well, density functional theory calculations actually tell us that the order should matter. So the chromium selenide termination is strongly dependent on the growth order. If you grow chromium selenide on top, it's going to grow chrome terminated, which means that the chrome moments are right up in contact with the bismuth antimony telluride. And actually, you also expect a slightly larger interface moment in the chromium. And those two combine to open up a gap and give you a net magnetization. On the other hand, if you grow chromium selenide on the bottom, it ends up being tellurium terminated at the interface. And then you get basically no strong magnetic interactions across the interface and no magnetic proximity effect. So having combined neutron reflectometry, transport data, electron microscopy, and element-specific information from X-rays, this is sort of, I think, the ideal approach of just sort of throwing everything in the kitchen sink all at one system and trying to really understand what's happening. Now, I want to then sort of finish up the examples section with one final case. And this is a case where we're really sort of pushing the limits of what we can detect. And this is another antiferromagnetic proximity effect. It's chromium antimonide, where you again have these spin polarized layers in your sample. And we're going to grow that next to bismuth antimony telluride. And this is work led by Qinglin He from Kang Wang's group once more. And you get these really nice high quality interfaces and some really strange electrical transport behaviors. So of course, the chromium antimonide doesn't really show anything interesting on its own. You have a non-hysteretic longitudinal magnetoresistance and a linear anomalous Hall measurement. You have basically no magnetization signal. If you grow bismuth antimony telluride underneath chromium antimonide, you get a larger magnetization, you get hysteretic magnetoresistance and a hysteretic anomalous Hall effect. And then if you sandwich the bismuth antimony telluride in between the chromium antimonide, what you find is a very strange anisotropic switching behavior in your longitudinal magnetoresistance, and you see a large anomalous Hall effect, even larger than in the bilayer case. And theoretical calculations by Genyin demonstrate that you are actually, at least theoretically, you should be inducing a series of topological transitions that alter the surface state as you go through the hysteresis loop, and that explains this anisotropic switching behavior in the longitudinal magnetoresistance. So of course, what we want to do is then bring in polarized neutron reflectometry to understand where this is this a real proximity effect, and what you see is a ridiculously tiny signal. This is the best we could do after about 5 days. So we measure. At this region right here, you see maybe a really small bump in the spin asymmetry. All the way out here, you maybe see another small bump in the spin asymmetry. And the best fit is to a sort of interface moment related to a magnetic proximity effect. It doesn't quite catch it here if it's magnetic chromium antimonide, but it's close. It definitely isn't uniform magnetization in the bismuth antimony telluride. But what this should really tell you is that after 5 days of counting on this, we got a very noisy data set. And so it worked, but barely. And clearly the problem that we often run into is that our data bar, our error bars in the neutron reflectometry data are just too large. And so how do we deal with that? So our uncertainties in neutron reflectometry are almost exclusively determined by counting statistics, i.e. how many neutrons did we actually count at a given angle? And so the answer is that we need a lot more neutrons. And the fortunate answer is we actually have a lot more neutrons than we're currently using. So a traditional design for a neutron reflectometer has a focusing monochromator at the front that then sends a specific wavelength at the sample and then bounces off into the detector. But the reactor gives you a huge wide band of neutron wavelengths, and we only pick a really narrow bunch of this. But in an ideal world, we'd like to take a wider band, say from 4 to 6 angstroms. So the question is, what if we took all these broad wavelength bands, sent them all towards our sample and sorted them out on the other side with a multiplexing detector? And so that's CANDOR. That's the new neutron reflectometer, just hopefully starting soon to do user measurements at the NIST Center for Neutron Research. And so the idea here is that on the back end, you have an array of 54 graphite crystals that are picking off individual neutron wavelengths and sending them into a bunch of different detectors. And so here you can see the detector response where each of the individual detectors picks out a different wavelength. And what this really gives you is 54 neutron reflectometers all stapled together. So that you can, and I know I'm late a little behind schedule here, so I'm going to fast forward a little bit, but the basic idea is you can then combine data from all 54 of these reflectometers to get something like a factor of 25 improvement in intensity. And this has a really important consequence of, if you look at the sort of traditional style reflectometer error bars in the black and green, or just the black here, you see that they're quite large, right? And they get really large the higher angle you look at. On the other hand, the CANDOR error bars stay really, really tiny out to extremely high angle. And so the Q range is much wider. And I think this is really going to change how we do these sorts of measurements in the near future. The other thing I think is going to have a really big impact is X-ray resonant magnetic reflectivity. Here I'm just throwing up a really quick example from Timo Kushel's group, where they take advantage of the really high intensity X-rays and the sensitivity to different elements to do really high precision measurements on proximity induced magnetization of platinum next to cobalt or iron. So this has traditionally been extremely hard to analyze, but it's been getting a lot easier. I think it's somewhat underutilized currently, although maybe people are doing things I haven't seen yet in topologically non-trivial materials. Okay, so thank you for making it this far. I just like to finish up by saying, hopefully I've convinced you that sort of depth and element resolve probes are really important components for probing these sorts of effects, but you have to be very careful about interpretation when you have confounding structural effects present. You want to combine as many techniques as possible, and I think that a number of new instrumental approaches are going to be really game-changing in the next few years. So if you want more reading on this, there are a number of really nice review articles that have come out recently that I highly recommend. I tried to thank everybody as I was going, but I want to thank everyone who made all this work possible. You know, many people contributed to all of this, and I am mostly just the guy that that does the neutron reflectometry for people with really nice samples. So thanks a lot. I'm happy to answer any questions.
Thank you, Alex. That's a fantastic overview and how you have to be very careful with these things and really to try to. I was not aware of the precision of some of those things that have to come in. So please, I haven't really seen any hands up. Or maybe I don't know if Branislav. Okay, let me see. Hang on, there was a hand up somewhere. Oh, the panelist. So Matthias, go ahead and ask the question, please.
Yes, thank you. So first of all, yeah, thank you for the great talk. I have one, it might just be a minor detail, but one thing you talked about the chromium antimonide on top of the topological insulator. And I think that is now known to actually be like an alter magnet and not an antiferromagnet. Does that somehow change the interpretation of like electrical measurements like anomalous Hall effect that you see in the system?
And to my, sorry, I missed a little bit of that. It's known to be a what?
an alter magnet. So it's like an antiferromagnet that has a spin polarization. So does that change the interpretation of this particular data set?
Oh, that's a good question. Chromium antimonide is pretty complicated. Not only that, but there is some evidence in another study we did that I didn't have time to talk about. There's some evidence that you actually change the magnetic state in the chromium antimonide as you interface it with these topological surface states. This has shown up in a number of different studies, actually. I think Nitin Samarth had a study on, I'm not sure if it was Nitin. There was definitely a study about how interfacing yttrium iron garnet with the topological surface states may actually change the magnetization in the yttrium iron garnet, not like, and the interaction goes both ways. So I think the answer to your question is yes. We tried hard to carefully look at, sort of control measurements where we look at, okay, what does the chromium antimonide do on its own, and then compare it to the bilayer, right? And so that's, I think the biggest point to make here is that the changes are significant when you start to get these interfaces. But of course, there's been a lot of discussion about why antiferromagnetic proximity effects work in the first place. Why do they exist?
Yeah.
And that actually may be why, right? The spin polarization in chromium antimonide may be super important to these effects. How much the topological surface state leaks into the chromium antimonide, who knows, right? Like unraveling the details of these interfaces is a theoretical study that I very fortunately don't have to do.
Okay. Thank you.
Thank you, Matthias. The other Matthias, the MM.
Thanks a lot for this super exciting talk. I have a question about this new instrument Candor. So essentially, when you want to use a different window for the wavelength, you get more flux. That's clear. But of course, you lose resolution. I mean, it's kind of a trade-off. So now you say like 2 angstrom is a good window to use, or 1 angstrom, or 1.5 angstrom. I mean, how do you choose how much more flux is worth having while not losing the resolution that you get from the broadening?
Right. So I think this is a result of poor pacing on my part, in that I ran out of time to really explain how Candor works. So the difference between spallation sources and reactor sources. So I work at a reactor source for neutrons. And that means we have a continuous stream of neutrons coming in, right? So at a spallation source, none of this really applies because they use time of flight measurements. And the time of flight measurements give you like basically energy, all the resolution you want, because you have very precise timing and on the neutron arrival. You are absolutely correct in general that a broader wavelength is going to crush your resolution. With Candor, we're cheating. So instead of putting a monochromator on the front end of the instrument, we have monochromators on the back end. So that's this sort of picture here where you have all these different array, like pyrolytic graphite monochromators on the backside, and they're all
parallel the different energies. Okay.
They're all stacked behind each other, and because the neutrons just pass through, you only get one specific wavelength. And so you pick them out one bit at a time. And so this is like a really nice way of preserving your resolution while at the same time getting a massive increase in flux. Now, the advantage of Candor actually is eventually we can also spread out the wavelength, the angles, because we should eventually support not just one bank of 54 detectors, but 20 different banks. And this should give us a factor of like 1,000 in intensity increase rather than just 25, but we're not there.
That's going to fry up the sample.
No. I think no worries. But that's really exciting. I think that's really, the only thing is that you cannot go skiing in between changing samples, but okay.
This is a real issue. Yeah.
Okay. Thanks a lot.
The samples are actually often
that's what
quite
global warming
radioactive.
is for, yeah. So Timo and then Gisela afterwards. So go ahead, Timo.
Yeah, thank you very much. Hello, everyone. Hello, Alex. Thank you for mentioning our X-ray magnetic reflectivity work. Yeah, and thank you for your nice talk. So, as you said that you have used, yeah, thanks, that you have used TEM to support the things that you observe. Have you ever talked to your collaboration partners that did this TEM images, whether they used the TEM itself maybe to identify a magnetic proximity effect? So if they have some kind of, yeah, different magnetic directions in the samples, different magnetic states, maybe it would be possible to see a different reflection of the electrons in that system, right?
So this is actually a little outside of my expertise, but I know that there exists a few ways of doing this, right? You have electron magnetic circular dichroism, which I think basically works like it's basically combining eels with polarized, spin polarized electrons to get basically element specific magnetic information. This is the dream, right? Is that you get like sub nanometer precision element-specific magnetic information from a TEM. My understanding, which I think is almost certainly outdated, is that they don't yet have the resolution you would want or the sensitivity you would want for a proximity effect, but I think they're making rapid progress. So I just may not have kept up. I don't know if this is possible yet, but that is definitely the sort of ultimate dream.
But there was no experiment in parallel to your investigations for a sample system that you have studied?
Not that I'm aware of. I think most of the stuff I've seen is all about like studying. I know people who studied, I think, LSMO using spin polarized electron diffraction in a TEM. I think I've seen a paper on this a while back, but like I think it's just, it tends to be noisy, and these are really, really, really hard experiments. So I don't think it's there yet, but I would love to be wrong.
Yeah, okay.
I would deeply love to be wrong.
Yeah, okay. Thank you.
Okay, Gisela.
Thanks for this very nice talk. I have a question concerning the samples. I think they have to be very large, or as large as possible.
This is a really good question. Okay. So the other advantage of candor that I'm hoping not to over-advertise is that it may be possible to measure smaller samples just by brute forcing the number of neutrons on the sample, right? If you get 3 orders of magnitude, assuming you can keep your signal to noise reasonable, you may be able to push down to like a square millimeter. Most of the samples I've measured over the last few years are somewhere between 5 by 5 millimeters to maybe 2 by 2 centimeters. It's very compatible with PLD measurements or MBE or PLD or MBE depositions. Yeah. There is an instrument at the Swiss neutron source, AMOR, that is actually vertically and horizontally focusing using some really exciting and new optics. And so they can, I think, get it down to, I want to say 2 millimeters horizontally and 1 millimeter vertically. And that, it's really, really cool. And the new instrument at the European spallation source, Estia, that of course does not exist yet, but they intend to basically build on the AMOR design. In fact, I think the AMOR is intended to serve as sort of a test bed for Estia. So you, in principle, should get all the focusing power of the AMOR instrument, but with all of the flux advantages of the European spallation source. So all of that's super exciting. My dream is to actually incorporate the candor detector design at a reactor while simultaneously incorporating these vertically and horizontally focusing optics on the pre-beam path. And so, like, in principle, then you're looking at, I think it should be possible to, on a 1 by 1 millimeter sample, get maybe a 2,000-fold increase in intensity relative to sort of the traditional design that's been dominant over the last 20 years.
But if you compare it to the TEM images, the TEM image is maybe the best image they get in the TEM, and you interpret the quality, or this, you say this is the total quality of the sample. Are you not nervous about this?
We're super nervous about this. And so our collaborators I want to give a shout out to Megan Holtz, who did these the TEM measurements for us. I can find it. Sorry, right here, right? So we were very nervous about this, and we had her check a number of different spots on the sample to get the thicknesses. And so the error bars, the sort of range I give right here is a 95% confidence interval based on the statistical sampling of the various points on the surface. So yeah, we're super duper nervous about that, and you can get into real trouble.
Yeah. And last question. Are you not nervous about the long range inhomogeneity, which reduces the definition of the incident angle?
Are you talking about in
so large
TEM?
Samples. If you have so large
so yeah, that's a great question. So inhomogeneity across the surface of a large film. So that's a very, very, very complicated and super neutron-y question. The answer is it depends a lot on the neutron correlation length. So the transverse size of the sort of coherent size of the neutron wave packet. This actually, I think, tends to be on the order of, I'm going to get this wrong. I want to say 100 microns laterally.
Okay.
It's not enormous. Longitudinally, like lengthwise, it can be quite a bit bigger, and it ends up being angle dependent. But in terms of transverse, I think it's not probing the entire sample at once usually. And so you're sort of getting a subset. And so like a little angle change or curvature, it might change the overall shape of the reflected beam, but it should be okay. If you are getting inhomogeneity that the neutron can detect, it will appear as an increase in the surface roughness.
Okay,
that is something that we do see a lot in specifically van der Waals type materials like topological insulators, like because they tend to form these sort of nanometer sized terraces on the surface. And so locally you get really, really smooth looking interfaces in the TEM. And I gotta find this. Hang on. This is like a pet issue of mine. Right. Okay. This right here. This does not look smooth, right? This looks like a real gradual slope. Over long ranges where you have these nanometer sized steps, it's not smooth. On a TEM level where you're probing like local behavior, it's super sharp.
Yeah.
And so you have to be so careful, right? So sometimes we end up in arguments about, well, how can we really constrain our interface roughnesses in the modeling? Do we say take a TEM measurement and constrain the roughness that way? Well, sometimes you can do that with topological insulators, usually not. Also X-rays, if you do an X-ray reflectivity measurement, the coherence length of the X-ray is different from the neutron. And so you may actually get the same thickness answer for X-rays and neutrons, but you may get different roughness answers. And so usually we treat the X-ray roughness as the lower limit for the neutron roughness because the wave packet is
thank you.
Yeah.
Okay. Oh, there's one more. I'm good. So let's wait for Igor will join us in a second. So Igor, go ahead. Can you ask your question? Oh, not sure if. Yeah, go ahead, Igor.
Okay. So what I wonder that when you actually put anything on the surface of topological insulator, there always exists question whether the surface states which actually make topological insulator by this topological insulator do not disappear. So what are the arguments that these states somehow show themselves, or at least make sure that the topological insulator remains topological insulator?
So this is a phenomenal question about which I know very little. Mark Stiles has very graciously attempted to educate me on this topic. So my memory is that you should definitely get a topological surface state that is well preserved if you have an interface between a topological insulator and a trivial insulator. And so that tends to be, I think, what is found. And there's a lot of evidence. So if you look, and I'm going to try and go way back. If you look way back at some of the spin orbit torque measurements, so here I just borrowed a figure from Peng Li's paper about this. Here they used barium iron oxide, and that is a really, really strong, like, insulating material. And they see really strong evidence that your spin orbit torque is heavily enhanced by the topological surface state itself, which implies that it does in fact exist. And I believe that Kang Wang's group, I want to say it was Hao Wu, had a paper in PRL that showed very similar things as Peng's paper, where they actually stepped through, I want to say it was the bismuth to antimony ratio, and showed that the surface state, like, you can actually go through the charge neutral point of the Dirac cone and demonstrate the existence of the surface state that way. In terms of conductive interfaces, it is harder to tell for a number of reasons, right? So not only is it harder, like, you don't necessarily, I think, expect the topological surface state to be unchanged in metallic to topological topological insulator interfaces. It may be different. And it may be gone. And of course, how can you tell if you're shunting half your current through the conductive layer, right? So the answer to that question is, I don't know, and we should ask someone who is better at theory. This is a real good question.
Well, actually,
Igor is a good theorist.
Question arose because you have different results when chromium layer lies on or not on the surface.
Yes, so in both cases, it appears that the chromium selenide is insulating, so far as we can tell. Like, there doesn't appear to be, at low temperature, there doesn't appear to be metallic shunting of the current from the topological insulator through the chromium selenide. And so we think the surface state is still there because the chromium selenide appears to be insulating. But of course, we have not seen the quantum anomalous Hall effect, right? So if you want to strongly argue that it doesn't exist, I will not be able to prove otherwise.
Okay, thank you.
Okay,
Kind of
Branislav
remains.
Branislav, can you unmute yourself? Maybe do you have a?
Yes. Hi everyone.
You got to turn on your camera too.
Yeah, can you hear me?
Yeah, you're going to turn on your camera if you like. You're in panelist now.
You're suggesting what?
If you want to turn on your camera, you can.
Oh, okay.
Panelist now.
Yeah, so I just wanted to chip in on this question. What happens when you cover topological insulator with different types of materials? So it's not that simple. For example, you mentioned the spin orbit torque. There is experiment by Otani in Japan when they cover a topological insulator with layer of copper to separate it from permalloy, hoping that they would have the simple picture of just a cone preserved. And you have a simple picture of cone just being open by supposedly magnetic field and breaking Otani's invariance. And then they see all kinds of strange things because they were shifting the Fermi level by doping. And they say, you know, oh, suddenly the cone disappears or the spin momentum locking is unstable. But these kind of questions do not can be answered rigorously, not by using intuition. And the rigorous way to answer them, and I actually sent you an email a couple of days ago about this, is to look at the spectral functions, exactly the same one that you would look at the surface of the bismuth selenium to vacuum, which was like the beginning of the whole discovery of realistic materials. But now you're calculating the spectral functions plane by plane inside. And of course, ARPES cannot access them because ARPES photons cannot penetrate below 2 nanometers. And so, like when we looked, for example, at cobalt bismuth selenium, as you anticipated, it gets really messed up because cobalt is metallic. It has metallic wave functions, which are going to try to penetrate into bismuth selenium. Bismuth selenium itself tries to dope itself into the bulk by evanescent wave functions. And when these two wave functions hybridize, and on the top of it there's charge transfer, that Dirac cone is extremely sensitive to charge transfer. So any charge going into the Dirac cone is going to actually push it down into the valence band. And what you will see is that there is no Dirac cone at the Fermi level anymore, let's say in the case of cobalt. Instead, it is buried into the valence band, and it's like half a electron volt below the Fermi level. And all of this stuff can be calculated in our nanoletters paper from 2016-17. And then the issue then becomes what happens when you put insulator. Naively, insulator should be the name of the game, because then you don't have to worry about apparently a charge transfer. And that calculation has been done by Kyung-Hwa Park. There was a PRB 2015, I think. And even in that case, it's not that simple as the previous question was kind of hinting at. So like when you put europium oxide on the top of bismuth selenium, even though there is no apparently charge transfer, there's some kind of polarization effects, and you actually get 3 Dirac cones. And they're also moving. So it's a very, like what I'm trying to say is that this simple picture, when you take sigma dot p Hamiltonian, and then you add a Zeeman term, which is where your all the images are coming from, is very difficult to justify once you go into like arbitrary combination of realistic materials and perform first principles calculations.
So
this is also what I was commenting, Alex, at the beginning when so Branislav, we're talking about you at the beginning before we started the whole thing, because he commented the discussion so Branislav has a very perfect code for that, to actually look into some of the issues that you're discussing, because he developed these fantastic scattering non-equilibrium functions that he kind of layer by layers and even put the different layers. So if anybody can try to answer these things, it's him. Yeah.
I think this is a number of extremely good points. You will notice that I very intentionally avoided talking about the details of the Fermi level and how like it may or may not be changed by all of the weird things we're doing to it in these heterostructures, right? These are questions you are far more equipped to answer than I am. And I think they're a good point, and we need to figure these things out. And, you know, I think there's a lot of fruitful discussion to be had.
Yeah, of course, there is a limitation that in all of our calculations, we assume that everything is perfectly clean. And that would mean, you know, that when you grow your stuff, it would have to be like, you know, perfect epitaxial, and that's not the real life. So like, what
that's not happening.
Yeah, of course. So like there is an extra layer, like everything I was kind of mentioning is insight from idealized systems when two perfect lattices match, and then you have some strain, but nothing like interdiffusion, vacancies, and all kinds of other junk.
It's worth pointing out that it's possible, right? I mean, the Takura group clearly managed to keep the surface state intact, at least in tellurium-tellurium heterostructures, right? I mean, it definitely exists because you see the quantum anomalous Hall effect in the zinc chromium telluride and the BST system. So it should be doable. We just have to find the right system and grow it well enough.
Let me also mention, like, just to conclude, is that there is a kind of always two proximity effects. In superconductivity, you have superconductivity going to normal side and normal side depleting the superconducting order parameter. By the same token, in these systems, if a magnet introduces magnetic ordering in the topological insulator, because it has metallic wave function, is going to penetrate to the other side. And then your magnet is going to be what theorists at least are discussing in the past couple of years, spin orbit proximatized. And for example, when you put cobalt next to bismuth selenium, you will see that few layers of cobalt would acquire topological spin texture. And that should play an important role, for example, in spin orbit torque or any effect where you believe that there is a non-collinear magnetism playing the role.
Right.
Like non-collinearity between spin density and magnetic moments.
This is for sure a good point, right? Like we talked about, the surface state leaks in and affect the behavior, like as I mentioned earlier, the study showing that it actually changes the magnetization in the magnetic behavior of YIG at the interface, right? It's very, very complex.
Okay.
Thanks a lot, by the way, for a very nice talk.
Thank you very much.
Yeah, that's great. I'm going to stop the streaming now, and